What are quasars and why are they so bright? When we look up at the night sky, the stars seem bright and close to us. But what if I told you that there are objects that emit more light than hundreds of billions of stars clustered together in a galaxy? These are quasars, some of the brightest and most mysterious objects in the universe. What are quasars? Quasars are the active nuclei of distant galaxies. They are at the center of massive galaxies and are powered by supermassive black holes. When matter, such as gas or stars, falls into a black hole, it is heated to extreme temperatures, creating the powerful radiation we observe as a quasar. Why are quasars so bright? The key to the brightness of quasars is the accretion disk surrounding the black hole. When matter accelerates and heats up in this disk, it emits huge amounts of energy in the form of light, X-rays, and gamma rays. A single quasar can be brighter than its entire galaxy and can even outshine the brightness of billions of stars. Where are quasars located? Most quasars are located at great distances from Earth. This makes them important objects for studying the early universe. The light we see from quasars has traveled for billions of years, allowing us to look into the past and see what the universe looked like in its early stages. Interesting fact: quasars also emit powerful jets, streams of particles ejected at incredible speeds close to the speed of light. These jets span millions of light years, affecting the formation of surrounding galaxies. Black holes. What happens beyond the event horizon? Now that we've mentioned black holes as the centerpiece of quasars, let's delve into their mysterious world. Black holes are regions of space where gravity is so strong that even light cannot escape it. How do black holes form? Black holes form when massive stars end their life cycle and collapse under their own gravity. This process creates a point of infinite density, a singularity, surrounded by an event horizon. What happens beyond the event horizon? The event horizon is the boundary beyond which nothing can escape. Once beyond the event horizon, matter and information are lost to the outside observer. But what happens inside? That remains one of the great mysteries of modern science. Perhaps there are other dimensions or new forms of matter beyond the event horizon. Some theories suggest that black holes may be portals to other parts of the universe or even to other universes. Environmental impact. Black holes don't just absorb matter, they also emit powerful relativistic jets, similar to quasars. These jets can burn gas in galaxies, suppressing star formation. The questions that remain: if we can ever get beyond the event horizon, what will we find there? Could black holes be the key to unraveling the nature of time and space? Pulsars and magnetars, stars with unusual properties. Pulsars and magnetars are exotic types of neutron stars that form after supernova explosions. They are unique in their characteristics and are among the densest objects in the universe. What are pulsars? Pulsars are neutron stars that spin at incredible speeds and emit narrow beams of radio waves. These beams resemble lighthouses that we can observe as they pass through our line of sight. Why are pulsars so unique? Rotational speed. Some pulsars rotate at speeds of up to several hundred revolutions per second. Accuracy. Pulsars are so stable that they can be used as space clocks for navigation and time measurement. What are magnetars? Magnetars are neutron stars with an extremely strong magnetic field that is trillions of times larger than Earth's magnetic field. This field creates powerful energy emissions that can destroy surrounding matter. Interesting facts about pulsars and magnetars. One of the most famous pulsars is the Crab Nebula pulsar. It is the remnant of a supernova observed on Earth in 1054. Magnetars can emit flares that are billions of times more powerful than solar flares. How are these objects related? Now that we've discussed quasars, black holes, pulsars, and magnetars, let's look at their relationship. Commonalities. All these objects are products of stellar evolution. They play a key role in the formation of galaxies and the distribution of matter in the universe. Differences. Quasars and black holes are associated with the active nuclei of galaxies. Pulsars and magnetars are the remnants of individual stars that have ended their lives. Each of these objects, quasars, black holes, pulsars and magnetars, opens a window into the wonderful and mysterious world of the universe. They show us how diverse and complex the cosmos is and make us think about our place in it. I believe that studying these objects not only answers fundamental questions about the nature of the universe, but also inspires us to keep exploring the unknown. Quasars demonstrate the power and energy of cosmic processes, black holes pose philosophical questions about the nature of time and space, and pulsars and magnetars are true natural laboratories of extreme physical conditions. Together they form a picture of the universe that we are only beginning to understand. Who knows what other discoveries lie ahead? If you want to learn more about such amazing phenomena of the cosmos, don't forget to subscribe to our channel, give us a like and leave a comment. Your interest and support inspires us to create even more interesting content.
Astronomy is the science of celestial bodies that helps us explore the universe, its structure, and evolution. However, one of the most challenging tasks astronomers face is measuring distances to objects in space. Whether they are nearby stars or distant galaxies, accurate distance data are important for understanding the structure of our universe and its dynamics. In this text, we will look at what methods are used to measure distances to galaxies and how they help us study the universe. Understanding the concept of distance in astronomy. Before delving into the methods, it is worth understanding what we mean by distance in the context of astronomy. Unlike terrestrial measurements, where distances are expressed in meters or kilometers, astronomy commonly uses light years, parsecs, and megaparsecs. A light year is the distance light travels in 1 year, approximately 9.46 trillion kilometers. A parsec is equal to about 3.26 light years. These units of measurement make it easier for astronomers to work with the vast distances in space. Measurement problem. Measuring distances in space is far from an easy task. The reason for this is that many cosmic objects, such as galaxies, are at such distances that traditional measurement methods that work on Earth cannot be applied. As a consequence, astronomers use a range of specialized methods to measure distances to stars and galaxies. Methods for measuring distances to galaxies. Parallax method. The parallax method is one of the oldest and simplest ways of measuring distances. It is based on observing the change in the position of an object on the celestial sphere if we change the point of observation. This method is effective for measurements at relatively small distances, such as for the nearest stars. However, for more distant objects, such as galaxies, parallax becomes insufficient because its effect is too small. Therefore, parallax is mainly used for measurements within our galaxy, the Milky Way. Why is parallax insufficient for measuring distances to galaxies? Cepheids. Cepheids are variable stars that change their brightness regularly. Importantly, there is a clear relationship between their period of brightness change and their absolute brightness luminosity. This fact allows astronomers to use the Cepheids as luminosity standards to determine distances. If we know the period at which the brightness of a star changes, we can accurately calculate its luminosity, and then, knowing the apparent brightness, calculate the distance. This method has been widely used to measure distances to galaxies as far away as 100 million light-years. For example, it has been used to measure the distance to the Andromeda Galaxy. Why do you think stars with variable brightness, such as the Cepheids, are useful to astronomers? Type Ia supernovae. Type Ia supernovae are explosions that occur in double star systems when a white dwarf, accumulating matter from its companion, reaches a critical mass and initiates a thermonuclear reaction. These explosions have nearly the same maximum luminosity, making them excellent candidates for determining distances. Just as with the Cepheids, knowing the apparent brightness of a supernova can be used to calculate its distance. Type Ia supernovae are considered an important method for measuring distances to the most distant galaxies at distances of billions of light-years or more. They play a key role in our current understanding of the expansion of the universe, as the detection of supernovae at different points in space has helped to establish that the universe is expanding at an accelerating rate. What conclusions can be drawn from the study of Type Ia supernovae for our model of an expanding universe? Redshift. Redshift is a phenomenon in which light from distant objects in space is shifted to longer wavelengths, that is, the red spectrum. This effect is related to the expansion of the universe. The farther away an object is, the more its light is shifted toward the red. By studying redshift, astronomers can not only determine the speed of distant objects, but also the approximate distance to them. The redshift method is particularly useful for studying very distant galaxies, such as galaxies in the far reaches of the visible universe. This discovery was one of the most important pieces of evidence that the universe is not just existing, but expanding. How does the redshift change as a function of the distance to an object, and what does this tell us about the universe? The thin line method. The thin lines method is used to determine the distances to galaxies when scientists examine the spectra of light that passes through a galaxy. Each molecule and atom has its own unique spectral fingerprint. Using this method, astronomers can accurately estimate the galaxy's removal rate and therefore its distance. This method not only helps to measure distance, but also to study the chemical composition of galaxies. What molecules and atoms are most often used by astronomers to determine the spectrum of galaxies? modern technology, and the future of measurement. With advances in technology, astronomy has gained new tools and methods for exploring the far reaches of space. Modern telescopes, such as the Hubble Space Telescope, help capture incredibly clear images of distant galaxies. In the future, our ability to measure the distances to galaxies is expected to improve even further with the development of new telescopes, such as the James Webb Space Telescope. In addition, concepts such as using gravitational waves to explore the cosmos also promise to radically change the way we measure and explore the universe. What new technologies do you think can help astronomers more accurately measure distances to the most distant objects in space? Measuring distances to galaxies is not just a technical challenge. It is key to understanding our universe and its evolution. Each method we consider provides a unique view of the cosmos, and each has its own limitations and capabilities. However, thanks to these methods, we have been able to learn more about the universe than we could have imagined a few decades ago. With each step forward in astronomy, we are breaking new ground and getting closer to unraveling the most fundamental questions, from how the universe works to how it will evolve in the future. If you are interested in continuing to explore the mysteries of the universe and learn new amazing facts about the cosmos, subscribe to our channel. We regularly publish exciting content that will help you delve deeper into the world of astronomy and beyond. Don't miss new videos, stories, and explorations that will open new horizons for you. Subscribe and stay up to date with the most interesting discoveries. The eternal mystery of the universe. When you look up at the stars, have you ever wondered, can the universe exist in an endless cycle of birth and rebirth? Our understanding of the universe has come a long way, from ancient myths to the Big Bang theory that dominates modern cosmology. But science is a living process, and from time to time new ideas emerge that change our understanding of the world. Today, we'll delve into the universal theory of retro-expansion, a fascinating concept that rethinks how our universe expands, contracts, and possibly cycles. What is the universal theory of retro-expansion? The universal theory of retro-expansion (UTRE) suggests that the expansion of the universe is not a linear process. Instead, it may involve cyclical phases of expansion and contraction, or even temporary backward motions where certain regions of space shrink or behave in unexpected ways. This theory challenges the idea of an infinitely expanding universe and offers a more dynamic, pulsating picture of the cosmos. Imagine a rhythm where the universe seems to breathe, expanding and contracting like a cosmic heart. Key ideas of the theory: cyclic expansion and contraction. Unlike the linear expansion described by the Big Bang theory, UTRE suggests that the universe moves through cycles. Each Big Bang may be accompanied by a contraction phase, what is sometimes called a Great Compression. These cycles can last billions or even trillions of years. Localized, retrograde motion. Certain areas of the universe may not follow the general trend of expansion. Gravitational forces or dark matter interactions can cause localized backward behavior where parts of space are temporarily compressed or stabilized. The dynamic role of dark energy. Dark energy, the mysterious force believed to accelerate the expansion of the universe, may behave differently over time. The theory suggests that dark energy may not be constant, but may be changing, causing fluctuations in the rate of cosmic expansion. How does this theory differ from the Big Bang Theory? The Big Bang Theory states that the universe originated as an infinitesimally small and dense object that began expanding about 13.8 billion years ago. Since then, the expansion has continued with acceleration due to dark energy. The universal theory of retroexpansion suggests a cyclic behavior or variable expansion rate, which could explain some anomalies in cosmic observations. The horizon problem. Why is the temperature of the universe so uniform over vast distances? Otter suggests that previous phases of contraction may have allowed energy to be more evenly distributed. Variability of dark energy. If dark energy is not constant, its fluctuations could have led to periods of deceleration or contraction. Anomalies of galaxy motion. Retrograde behavior could explain why some galaxies appear to defy traditional models of expansion. What evidence can support this theory? Although Otter is largely hypothetical, a few observations can support it. Relic emission, CMB. Residual glow from the Big Bang may contain subtle patterns or temperature variations indicating previous cycles of contraction and expansion. Large-scale structures. The distribution of galaxies and galaxy clusters in the universe can show traces of past contractions, such as unusually dense regions or patterns not consistent with linear expansion. Gravitational waves. Gravitational waves not only confirm major events, such as black hole mergers, but can also provide clues as to whether there have been phases of contraction in the history of the universe. Dark energy measurements. If astronomers can observe fluctuations in the strength of dark energy over time, it could support the idea of a variable, nonlinear expansion process. Problems and criticisms. While the universal retroexpansion theory is inspiring, it faces several obstacles. Lack of direct evidence. The Big Bang Theory currently has more evidence, such as redshifted galaxies and relic radiation. UTRE needs more concrete data. Complexity of retrograde dynamics. Explaining localized retrograde motion in a universe dominated by dark energy and dark matter is a challenging task that requires more advanced simulations and observations. Competing theories. Other models, such as the Big Bounce theory or the multiverse theory, also attempt to answer questions about the origin and fate of the universe, sparking scientific debate. Significance of the theory. If Otter proves to be correct, it could overturn our view of the universe and its ultimate fate. Here's how. A new cosmic chronology. Instead of a single beginning and end, the universe could be an endless cycle of birth and rebirth. Physics revisited. The laws governing cosmic expansion may need to be adjusted, especially with regard to dark energy and gravitational forces. Possibility of eternal renewal. Cycles of expansion and contraction may mean that the universe has no final death, only transformation. A new way of looking at the cosmos. The universal theory of retroexpansivity invites us to rethink the complexity of the universe. It reminds us that our understanding of the cosmos is constantly evolving, and that new ideas, even controversial ones, push the boundaries of science. As we explore the universe, theories like Otter inspire us to ask deeper questions. Are we part of an infinite cycle? Could the cosmos one day reverse its motion? Or is this just the beginning of understanding something much bigger than we can imagine? Thanks to our viewers for the inspiration for this journey into the world of universal retroexpansive theory. Especially our friend from Brazil who suggested this topic. If you enjoyed this exploration, subscribe to our channel and join us to explore other cosmic mysteries and discoveries.